In this presentation, I want to discuss a security vulnerability that I have found in implementations of HTTP strict transport security, or HSTS, and also discuss some more general issues with HTTP and HTTPS and the mixing of secure and insecure contexts. This presentation was originally given at the Nullcon Security Conference, but unfortunately the talk was not recorded, and therefore I am making this video. So originally in the World Wide Web, there was the HTTP protocol, but it was without encryption. But in 1995, Netscape, back then the leading browser vendor, introduced what they called SSL. Today this is known as TLS for complicated reasons, and it's still confusing people, and HTTPS, which is a version of HTTP with SSL on top. And SSL and HTTPS provided encryption, so no one could sniff or see your data on the wire. It provided integrity and authentication, so you knew who you were talking to, and you had a guarantee that the data was not manipulated on the connection. But also SSL has a few problems. First of all, it was expensive because you had to buy a certificate from a certificate authority. This has today been fixed thanks to Let's Encrypt, which is now providing free certificates. But also SSL was introduced optional security, so we didn't replace the insecure HTTP with a more secure version, but we added an optional secure version of HTTP. And this is what this talk is mostly about, HTTPS and HTTP, they are mixing secure and insecure contexts, and this causes all kinds of problems. Now, mixing secure and insecure contexts. When I prepared this, I thought it's not the first time that I'm talking about this, and I was previously involved in a research project around StarTLS, which is commonly used for email protocols. And we discovered also a lot of problems that are around this mixing of secure and insecure contexts. It's not what I'm going to talk about in this presentation, but I have given a presentation about that before, and there's a web page about what we found, and I will put links to that in the description. So today I want to talk about mixing insecure HTTP with secure HTTPS. One problem that often comes up there are cookies. So cookies are essentially the state mechanism we have in the web. So when you log in somewhere, you have a session, and this session is implemented by using cookies. And these cookies are bound to either the host name, so something like www.example.com, or they can also be bound to a whole domain or covering multiple subdomains. So you could have a cookie for .example.com, and that would be valid for all its subdomains. A very obvious problem with cookies and mixing these contexts is that you can have a situation where you set a cookie over a secure HTTPS connection, but then you have an insecure HTTP connection, and as the cookie is not bound to the protocol but only to the host name, the cookie will get transmitted without encryption and can be seen by an attacker. This was already addressed very early with the cookie secure flag. So in 1997, RC 2109 says, optional, there's the security attribute with no value directs the user agent to use only unspecified secure means to contact the origin server whenever it sends back this cookie. That sounds a bit unclear, like unspecified secure means, but essentially what it means today is to use HTTPS. The user agent, possibly under the user's control, may determine what level of security it considers appropriate for secure cookies. So that's also very unclear. But we have somewhat better standards today. So in RFC 6265, which was published in 2011, it says The secure attribute limits the scope of the cookie to secure channels, where secure is defined by the user agent. When a cookie has the secure attribute, the user agent will include the cookie in an HTTP request only if the request is transmitted over a secure channel, typically HTTP over TLS or HTTPS. So that's a bit more clear. It still leaves some wiggle room, but essentially what we do today is if we have the secure flag, then the browser will make sure that the cookie is only transmitted over an HTTPS connection. Now, this RFC goes on to say, although seemingly useful for protecting cookies from active network attackers, the secure attribute protects only the cookie's confidentiality. An active network attacker can override secure cookies from an insecure channel, disrupting their integrity. Now, what this is saying is, that even if this flag protects you against someone reading a cookie that has been set secure, you can still have a situation where an attacker may set a cookie that then overrides your secure cookie. So that can also cause security issues. And only very recently we got a fix for that, and that is still in draft state, but you can now use some prefixes. One is the host prefix and the secure prefix, and they address this issue. So what they do is you can only set a cookie with these prefixes over an HTTPS connection. So that means over an unprotected HTTP connection, it is not possible to set a cookie with that name. So that is a very nice protection. It's still just a draft, but you should use it. And the host prefix provides an even better protection because that makes sure that the cookie cannot be set from another subdomain. This is, for example, very relevant because subdomain takeover vulnerabilities are extremely common. So if you can use that, and if you need a cookie only on one host, you should use this host prefix. Otherwise, you should use this secure prefix in addition to the cookie secure flag. But now, just because we have a secure flag for cookies, it does not necessarily mean that everyone will use it. And back in 2008, I was studying computer science and I wrote my midterm thesis and I wrote it about this topic. And when I prepared this talk, I kind of reviewed it and I was actually quite happy about what I wrote back then. A lot of it is still kind of applies today. Back then I found and reported various PHP applications that could be attacked with this cookie issue. Some of them fixed it, others didn't. And I also described a practical attack back then that was possible on the eBay website. 2 years later, someone published the Firesheep plugin, which was essentially, it wasn't really a new attack, but it was a tool that made performing these cookie attacks much easier, and that gave the issue a lot more attention and caused more people to fix it. Cookies have some other security features that are not related to TLS or HTTPS, but they're still in most situations useful. One of them is the HTTP only flag, which says that this cookie can only be transmitted through HTTP, but you cannot read it from JavaScript. This is also relevant because this protects against speculative execution attacks like Spectre. So there's a recommendation document from Google where they say to protect against Spectre, one of the things you should do is also you should set this HTTP only flag. And another thing is the same site attribute, and that protects against cross-site request forgery attacks, which is a different topic, but usually you should also set this, and you should usually set this to the value lax. The value strict is a bit more problematic with session handling. So usually, if you have a secure web application, this is roughly how your cookie should look like. So you have this prefix. If you can, you use this host prefix, which means the cookie will only be valid for this domain. You have to set a path if you use one of these prefixes, but in many cases the path will just be /, which means it's valid for the whole domain or for the whole host name. Then you have the secure flag, and then you have this HTTP only and same site flags. So that is a well set secure cookie in a modern day web application. But cookies are not the only problem of mixing secure HTTPS and insecure HTTP. Another problem are redirects. What we commonly do this day is that if a user surfs to a web page with HTTP in front, then it will just be redirected to the HTTPS version, because almost everyone has now moved to HTTPS by default. And on a technical level, this happens with the HTTP, with a special HTTP code, 301 usually, and the location header, which just redirects the client to the location on HTTPS. The problem with that is when we redirect from HTTP to HTTPS, then the redirect is not protected. It's still over HTTP, obviously, and so an attacker can manipulate that. And that is an attack that is called SSL stripping. It was discovered and presented by Moxie Marlinspike. There's a presentation about it. I will also put a link to that video. And that was discovered in 2009. So essentially, a network attacker can prevent the redirect from happening and serve a fake web page over HTTP and then do all kinds of attacks. Now, speaking of redirects, something I also see quite often is that people do something like this. Like they have a redirect from HTTPS, their domain name, to the www version of their domain name, but this redirect first goes from HTTPS to HTTP, and then they redirect back from HTTP to HTTPS. This can also be attacked by SSL stripping, so this should be avoided. Don't do that. Like every redirect, it should first go from HTTP to HTTPS and then never go back to HTTP. So how can we fix this SSL stripping attack? In response to that, a new feature was introduced that is called HTTP Strict Transport Security, or HSTS. This is specified in RFC 6797 and was published in 2012. And this is how it looks like. It's an HTTP header that is sent by the server or website, and it says strict transport security, and it has a few parameters and flags. So one flag is max age, that just means how long the browser should store the setting. So in this case, this is set to a year, like this is a value in seconds, and you can calculate that this is a year. But that means it expires. So what does that mean? It means if a browser sees this HSTS header with this value, it means it stores for this amount of time that this web page should only be accessed over HTTPS. So every attempt to connect to that web page over an insecure HTTP channel will automatically in the browser be redirected to HTTPS. But also it means that this setting expires after a certain amount of time. Now, if you think about time, like how do you set the time on your computers? What usually happens is that you have some daemon or some application that sets the time with the network time protocol, which is an internet protocol to set your time. Unfortunately, NTP is also insecure by default, and it didn't have any proper encryption or TLS support until 2020. Like it had an old encryption mode, but that was either insecure or it needed a pre-shared key, which is very impractical. And so you can attack this and set the time of a computer when you have access to the network. And there was a very nice attack that was presented in 2014, which was called the DeLorean attack. You can use NTP to send a computer essentially into the future by manipulating its time. And then by that you can expire HSTS policies, and thereby you can force HTTP connections again. There's a presentation of that from Black Hat. I will also put that in the description. Luckily today we have a secure version of NTP. There's the NTS protocol, or Network Time Security, that was specified in 2020. Unfortunately, of course, it's still optional and it is usually not enabled by default. So whatever software you're using to set the time off on your computers, you should enable this network time security feature. Another potential problem with HSTS is that it is a trust on first use mechanism. So once you connect to a server once, your browser will see the HSTS header and will know, okay, now I should connect only via secure connections. But you still have kind of a first connection problem. Like the very first connection may be unencrypted and could be manipulated by an attacker. To address this, there's a possibility in HSTS to preload your domain. So you can add a flag preload, and then there's a web page that is operated by Google where you can ask to add your domain to the HSTS preload list. And that is just a list of domains that is hard-coded into the browsers that say we always want our connections to be HTTPS, and we want that to be enforced by the browser. Right now, this preload list has 140,000 entries. It's around 15 megabytes uncompressed, 1 megabyte compressed. So this is still kind of manageable, but you can see that at some point there is a question whether this preload list can grow on forever or whether we need a different mechanism. And there are discussions among browsers what to do about this, but right now it is still possible for basically everyone to get added to this preload list if you want to. You just need to implement this header and this flag. There's another flag to HSTS which is called include subdomains, which does, as you might expect, define whether the policy should include subdomains or should only be valid for a certain host. And in last year, for some unrelated reason, I was confronted with this and I thought, how exactly does this include subdomain flag in HSTS work? And I thought a bit more, and then I tried a few things, and then I thought, no, this does not look right. Like, there's a problem here. So assume the following. We have a web page that, let's say it's HTTPS example.com, and that sets an HSTS policy with include subdomains. So the expectation is that, yeah, we now have an HSTTPS policy that is valid for all the subdomains of example.com. So example.com is completely protected and no one can connect over HTTP anymore as soon as they have seen this policy. Now imagine we have a subdomain of example.com, which we will just call sub.example.com, that sets an HSTS policy but without include subdomains. Now, which policy does it apply to a subdomain of that subdomain, like sub.sub.example.com? And can you open that subdomain over insecure HTTP? It turns out like the standard says no, you cannot, that should be blocked. Chrome also blocks it, but Firefox versions before version 122 opens it. So even though you had a HSTS policy on the main domain with include subdomains, you still could have a subdomain that could be opened by the browser. So essentially what happens here is in these older Firefox versions, any subdomain with an HSTS policy without this include subdomain flag disables HSTS for all subdomains of that subdomain. And that I found really the most shocking thing about that even worked with preloading. Because like I had the assumption if I preload a domain, in this preload list, like it's hard-coded into the browser, then the browser will just never connect over an insecure connection to that domain. And it turned out with this issue, you could kind of bypass that in many situations. The good news is the Mozilla developers immediately agreed that this is a vulnerability and that this needs to be fixed. So this is CVE 2024-0753, and it is fixed in Firefox version 122. And if you regularly install your update, you should already have this fix, obviously. I looked at a few other clients, also non-browser clients, and figured out that wget is also affected, like the command line tool to download things, but it has a very low impact because you usually don't have any sessions or anything and cookies in wget. I mean, it supports cookies, but you usually don't use that. So this was fixed by wget also, but the developers of wget said that they consider this to be a very low severity issue and they wouldn't handle it as a security issue. And I agreed to that. Like, I agreed with them that this has a very low impact. So why is this issue a problem? Now we're back talking about the browser, where I think it's a severe problem. Imagine the following. You have a domain HTTPS example.com that uses HSTS, includes subdomains, and possibly even preloading. So your expectation is everything on that domain is secure. Then you set a cookie, and you may set a cookie for the whole domain, like scoped for our subdomains. You can do that by setting a cookie for .example.com and without the secure flag, because your thinking is, I already have HSTS that protects me. There are no insecure connections, so I no longer need this secure flag. And then you open a subdomain that also has HSTS set, but it doesn't have this include subdomain flag. Then the attacker can first send you to this subdomain, which essentially disables the HSTS policy for all these subdomains. And then the attacker sends you to one of these subdomains and just redirects that request to an attacker-controlled server, and then the cookie is transmitted in plain text and the attacker can read it. In preparation for this talk, I wanted to look whether I find any host where I could show this attack, and Netflix.com actually had all the conditions for this attack to work. It had a cookie that was scoped for the whole domain. It had a subdomain that had an HSTS policy without include subdomains. So yeah. You may wonder whether I have reported this to Netflix. The answer to that is no. And I mean, I usually support responsible disclosure, but in this case, I really saw no practical way to report this, because this is the security TXT file from Netflix, and the only contact to their security team is their bug bounty program on Bugcrowd. And that's not good. Like, you shouldn't have a bug bounty program as your only security contact. Why is that? So from my experience, bug bounty triagers, like the people working for these bug bounty platforms, they are trained to reject as much as possible. That's very sad, but that's really my experience. So whenever they get something that looks complicated or they don't understand, they will reject it. And technically, it's not really a vulnerability on Netflix.com. It is just a non-ideal configuration. So this is something you may want to communicate to a security team, but you probably wouldn't expect a bug bounty for it. And also, this bug bounty program had a rule that it said, when you participate in this program, you're not allowed to disclose anything. So if I had submitted it there, I would not be allowed to talk about it here. So yeah, I decided eventually to just not disclose it to them. Yeah, so in preparation for this talk, I wanted to create a demo. And I tested it. And then I first tested it with Firefox 121, which is the vulnerable version, and it worked as expected. Then I tested the demo in Firefox 122, which was the version that was supposed to be fixed. But my demo still worked. That was unexpected. So why was that? So if you implement an attack like this, you need to send a user to various other web pages. So how can you do that? One option is to use iframes. It's a very common way, like you can have an iframe that is only 1 pixel size, so you can load any kinds of web pages and the user will not notice that. But Firefox actually has implemented HSTS in a way that sub-resources, and iframes are sub-resources, cannot set HSTS policies. And this was actually an attempt to fix another bug that also undermines HSTS, and it didn't really fix that bug. Like, I'm not really sure what they were thinking there. It all not ideal. Like, and the background of this is like there's a problem that Firefox has only a very limited list of domains it stores HSTS policies for. And by just sending a user to many web pages that load HSTS policies, you can sometimes force Firefox to drop some of these policies, which is not great. And yeah, but they don't really have a good solution for that right now. And in this context, this sub-resource thing was changed and introduced another problem. Even before that, Firefox used something called partitioning for sub-resources. And this is kind of an anti-tracking mechanism. They do the same thing for cookies. And what this does is that if you load a sub-resource like an iframe from one domain from another domain, then the cookie will be saved only for that combination of one domain loading the other domain. And this is so you cannot track people over third-party cookies over multiple sites. And they did the same for HSTS because in theory you could also use that for tracking. Unfortunately, while this may make tracking a bit more difficult, it introduces some more security problems with HSTS, and right now HSTS is implemented in Firefox in a way that is not according to the spec and also introduces additional security problems. And yeah, I'm not happy about that, but it seems right now that this is here to stay. So yeah, HSTS is generally a good feature and you should absolutely use it if you operate any web pages. But its implementation is not necessarily robust. In particular, in Firefox, there are a few problems. The main bug I described earlier was fixed, but as I said, there were some other problems. Yeah. Now I want to show a demo. I was able to implement this in a different way, that the demo actually works on the vulnerable version and does not work on the fixed version. And I'm going to show you that now. So here we have a fresh installation of Firefox 121, which is the last version that still had this bug. And as you can see here, Firefox wants me to update it, which we will of course not do right now. So first of all, we need to set these cookies that we want to attack. And as I said, we want to test this on netflix.com. So we just open netflix.com. And then we click accept here. So we accept all the cookies that Netflix wants to set. And then we close that again. And then we go to the next step. Now there's the subdomain issues.nrd.netflix.com that I don't know what exactly that page does, but it has an HSTS policy that does not have include subdomains. So now we have a situation where netflix.com set HSTS for all its subdomains, but this subdomain sets HSTS without its subdomains. And we open that, and yeah, it redirects us to some other page, which we can ignore and close it again. And now we have a situation where the attacker can redirect us to an unencrypted page, which he then controls. He can redirect this, for example, via ARP spoofing or DNS manipulation or some other methods that you can use for a man-in-the-middle attack. And if we open that page, we can see, okay, this is an unencrypted HTTP page. It is controlled by our attacker. And we can see here that the attacker could read out some cookies. So this example page here is just showing the cookies to the visitor, but of course the attacker could also send these cookies to himself and then maybe perform an attack based on that. Now we repeat all that, but with the current version of Firefox where this bug has been fixed. So again, we will close that. We will go to netflix.com and some cookies get set. Then we again go to that subdomain that has this policy without include subdomains. And then we do the same as before. We open this attacker-controlled HTTP unencrypted web page, but now we can see, okay, Firefox is blocking this request because now HSTS works properly. And if we zoom in, you can see that this site has a security policy called HTTP strict transport security, which means that Firefox can only connect to it securely. So yeah, after this bug has been fixed, this attack no longer works as we expect. Finally, I want to give you some recommendations if you're a web developer, what you can do to improve the security of your HTTPS connections. So generally, yes, you should use HSTS and you should always set the include subdomains flags because that always makes sure your policy is applied as widely as possible. You should use HSTS preloading, particularly for important domains. I'm not sure if I should recommend everyone to use preloading because then eventually this preload list may get too big, but particularly if you offer a service where security is important, then you should consider using preloading. Even with HSTS, you should use other tools to prevent any plaintext leakage. You should use redirects, like always redirect all requests from HTTP to HTTPS. And if your main web page is on the www subdomain, you can consider doing something like this, that when someone goes to your main domain, you first redirect to the HTTPS version of that, and then you redirect to the www version. Why is that? That makes sure that actually your HSTS policy will apply to all subdomains and not just to the www domain. You should avoid these insecure redirects that I explained earlier. So you should never have a chain of redirects where it goes from HTTPS to HTTP and back to HTTPS. And for your cookies, you should always set the secure flag, and HSTS is really no excuse for not having it because, as I said earlier, HSTS is not necessarily robust, so you cannot rely on it. You should use this host prefix if possible and this secure prefix otherwise, even though it's just a draft, but this is a very useful feature. And finally, a recommendation for users. If you want to be protected from all these issues, even if web pages are not implementing this in an ideal way, you can enable the HTTPS only modes in your browser. Most modern browsers have some kind of feature where you can say, I only want to connect over HTTPS, and every time I open an HTTP site, I have to manually approve that. That increases the security a lot and is really a recommended thing to do. Thanks for listening to this presentation. I hope you found it interesting, and if you have any questions, you can write them in the comments.